is the expectation value of the separation between two identical particles. All right, and what it says is that if, let's see, if we assume a wave function that's symmetric, right, then what we find out is that the expectation value for the separation between those two particles is closer together. And if we assume that the total wave function to begin with is antisymmetric or minus, then the expectation for the distance between the two particles is bigger. And that would be, well, I want to be careful, all right? Because right now, and I know I said fermions and bosons because I want to introduce those ideas into it.
Side negative, side positive.
So for now, so I think it's better if we don't say fermions and bosons. For what we say is like the symmetric spatial wave function is a plus, and then the antisymmetric wave function is a minus, okay? Okay.
Yeah, I'll write down side pluses and minuses.
Okay, so now what we're going to do is now we're actually going to talk about a physical case, and we're going to keep that idea in mind. And what we're going to do is we're going to look at helium. All right? So let's look at helium. All right? And helium has the nucleus, and then it has 2 electrons. So here's electron, and I'm going to label it. All right, which you can't do, right? But remember, what we're talking about are these two wave functions, the symmetric and the antisymmetric, only because we got into that problem with quantum mechanically. We could not label.
Could I just paint them white?
That's right. We can't label identical particles. They're indistinguishable. All right, and as a result, we got the 2 different types of wave function. Anyway, it's a very nice argument having to do with that with that operator that switches the labels. Remember, we found the eigenfunctions, and what we found out is the eigenfunctions are the operator that switches the label have to come in 2 different flavors, symmetric and antisymmetric, with respect to the exchange of those. And then what we also argued is that because that operator commutes with the total Hamiltonian, that means they have to share the same eigenfunctions. All right? And what we know about the eigenfunctions of the parity operators, they have to come in those 2 different flavors. So therefore, what we know is that the eigenfunctions of the total Hamiltonian has to also come in those 2 flavors, because those are the eigenfunctions of the parity operator.
Is it the same parity operator from CP violation?
No, no. Okay, so I say parity and I have to be careful. It really isn't the parity operator, it's the exchange operator. So if I keep saying parity operator, I'm wrong. Right? This is the exchange operator, and I know I keep saying parity all the time. Okay, so we're definitely talking about the exchange operator. Everybody got this story? It's an important story. Eigenfunctions of the parity operator are symmetric and antisymmetric wave functions. I just said parity. Eigenfunctions of the exchange operator are symmetric and antisymmetric. The exchange, I'm saying it here. I'm going to say it the most clearly I can say it. The eigenfunctions of the exchange operator we showed are symmetric and antisymmetric. We also showed that the exchange operator commutes with the Hamiltonian. Therefore, the exchange operator and the Hamiltonian share simultaneous eigenfunctions. Now, if the eigenfunctions of the exchange operator are symmetric and antisymmetric, that means those must be shared with the Hamiltonian. So therefore, for the Hamiltonian of these 2 electron systems, all right, that Hamiltonian must also come in 2 different types, which are the symmetric and the antisymmetric. Okay? Okay. Well, the next step that Griffiths did is he looked at the calculating the expectation values between all those different cases, and that's what we talked about. We talked about when we had the symmetric eigenfunction, it essentially lets those 2 particles get closer, right? Because the expectation for the distance between them is smaller. And for 2 identical particles, but in an antisymmetric wave function, it means that those particles stay a little bit further away from each other.
I see it somewhere that for the anti-symmetrical, the acting like as a repulsion force.
Yes, yeah, we're gonna get to that.
Symmetrically acts
Yep.
like
Yeah, kind of like pushes them apart. All right, but let's now jump to helium. All right, and what we're going to do is we're going to look for the total wave function, but it's just the electronic wave function. In other words, I'm not going to be looking at, not including in my wave function at all the proton, the nucleus.
that.
All right.
The repulsion between the two electrons.
I'm just looking at the wave function describing the two electrons. All right? And so it's definitely it's two identical particles. All right? And so when I describe these two and their electrons, the first thing I'm going to look at is psi of the space. And when I mean psi of space, it's like x1, or let's say r1 and r2. Well, in the example that Herbst did, he kept it one-dimensional, x1 and x2. All right? And this is equation 5.22. This is related to equation 5.22. Well, to be specific, what 5.22 does, it calculates the expectation value of x1 minus x2 quantities squared. That's what 5.22 does. It calculates the expectation value for this. And what we know now is that this has to come in two different flavors. It has to come in a psi space positive, and then it comes in a psi space negative. Right? And so for this expectation, what 5.22 shows, and this is kind of, I think this is going to work out, that the psi positive lets electrons be closer, and the psi negative has electrons further apart. And what I mean by that is when you calculate the expectation value, this one's smaller and this one's bigger.
And they're on either side of the classical.
And they're on either side of the classical. The classical's right in the middle. Okay? But then here's, and so I think I was also confusing last time, not only about the parity operator, and it should have been the exchange operator. All right? But I was also a little bit confusing by introducing the fermions and boson ideas a little too early. All right? And so notice I haven't done that at all yet. All right? Okay. So what we're really just talking about so far in that whole discussion is the spatial wave function. And what the exchange operator commuting with the Hamiltonian says is that the total wave function has to be symmetric and antisymmetric. All right, but right now I have a total wave function for the two electrons in helium, but do I have a total wave function yet if I just have the spatial part of the wave function?
No.
And the answer is no, because I have to include that other linearly independent space, and that's the spin. Okay, so I've got to multiply this times the psi of the spin. Okay, now, for two electrons, or two particles, right, two spin-half particles, do you remember what type of spin states I could have? What if the spins were both aligned?
1.
Okay, that would be a total spin of 1, but then how many projections could we have?
3.
So 1, 0, minus 1. So we called that the triplet. And that was a symmetric wave function or an antisymmetric? Do you remember?
That'd be symmetric.
Okay, it would be symmetric, yeah, they're both up. And then,
Okay.
well, they're
They're
up
both
and
up
down,
and
and then it's a plus, a down and up. So to write it out,
Yeah.
Because it could be either way.
so recall, here's what we did. For two spin-half particles, so here's a spin 1 and a spin 2. what we wanted to do is we wanted to, and they both equal a half. What we said is S1 plus S2 is greater than S total, which is greater than or equal to the magnitude of S1 minus S2. So this is 1 is greater than or equal to S total,
It's the absolute value of S1
which is greater than or equal to 0. Okay? Okay, so in other words, the total spin can be 1 or this can be 0. MS for this one is minus 1, 0, 1, and then MS for this one is just 0. So here's how we construct it, all right? Let me see if we can do it. We did something like this. The 1, 1 equaled, we did it two different ways, a half, and then a half and a half. So this is a spin of a half with a spin up, and that spin of a half with a spin up. Which in the book, we took the shorthand notation, and up and an up. Right? So the up essentially assumes the spin of a half, it's just the projection. Right? Then we also had the 1, 0 equals, and it was 1 over radical 2, and I'll go to that type of notation just to save some time. It was an up, down, plus a down, up. All right, and then we had the 1 minus 1, and that just equaled down, down. And this was called the triplet. This is called the triplet. Okay, then we also had the singlet, the 0, 0, and that equaled 1 over radical 2, up, down, minus down, up. All right, and you can see that this clearly is the negative. This is the,
When you do like,
on the exchange of electrons, this gives you the opposite. So this is the singlet. The triplet is symmetric. The singlet is antisymmetric. Okay? So what we have over here, the possibilities are, we can have a psi plus or a psi minus. And then over here we can have a psi spin plus or the psi spin minus. So that's symmetric, antisymmetric, symmetric, antisymmetric. Right? But now I'm going to throw in that last part that indeed we are talking about electrons. And so what electrons are fermions. All right? And therefore the total wave function has to be symmetric or antisymmetric?
Anti-Semitic.
Antisymmetric. So psi total has to be antisymmetric. So not just the space, not the spin, but the total has to be antisymmetric. So what are the possibilities that I could make to make an antisymmetric wave function based on these four cases?
You're going to have plus then minus.
Okay, so I could have a psi, I'll write it in psi space plus times a
Psi spin minus.
psi spin minus, and that's good. This is good. Or I could have
Psi space minus.
psi space minus, and then over here go psi space plus. And that's good.
Second one spin.
That's
As long
psi
as
spin.
it's- As long as the spin, as long as one's positive, one's negative, you get asymmetric.
Right. Yep, it's just like any other
As long as
function.
It's an even and odd.
It's even an odd argument. Okay? Okay, now watch. The antisymmetric spin was what? The singlet or the triplet? So this was the singlet. So this was the singlet. And what was the symmetric spin? The triplet. Okay? Now, here's the whole crux of Hund's rule. So these are two wave functions that we're going to get. We're going to do it for helium in a second. All right? But these are the two total wave functions you can get. Okay? This is the singlet. This is the triplet. which wave function let the electrons get closer together? This one or this one?
With the symmetric.
The one with the symmetric spin, right? So electrons closer. And then this one is the electrons further apart. Everybody agree?
Well, the side plus spin gives you closer, that would be the other way around.
It's the space, so.
What's that?
If you said side plus for the spin would bring you closer.
No, yeah, no.
But
it's
the
The
straight.
spin has nothing to do with space.
You said spin. yes.
Period. Oh, I said the wrong word?
Yeah.
Okay, sorry about that. So the antisymmetric space lets the electrons get closer together. Right? This is the result we got over here. The spatial part. So this is 5.22, just had to do with the space. So here we go. Here. That's the space part. Okay? And then all of this, if you want, is the spin result. And now we've got to kind of tie everything together. So we made our antisymmetric wave function the way we did it with the symmetric space, antisymmetric spin, symmetric space. Okay, we now know that the antisymmetric spin is a singlet, the symmetric spin is a triplet. And then we then use 5.22 to show that the electrons are closer together in this wave function, and the electrons are further apart in this wave function. Okay? So, let's now look at the total Hamiltonian. The whole total Hamiltonian is essentially equal to the total energy. And that equals EK of electron number 1 plus EK of electron number 2. Right? But what other energy do I have?
Rotational?
I mean, not just kinetic, yeah, potential.
I have the potential energy, right? So I'm going to have the individual plus, you know, the two potential energies, EP1 plus EP2. But I have one more potential energy,
The repulsion.
and that's the repulsion between the two electrons.
Okay.
Okay, so this is EP electron interaction.
What if we ignore that for now? Would that make our life easier?
Yeah, but it's not right. All right. So what we don't have. So we're at a point where we don't have to ignore it. All right, and we don't ignore it for this point that we want to make. Okay. What is the form of the potential energy between the two electrons?
Coulomb's law.
Okay. So how would I write it?
Okay, can you?
I agree. It's K. 1/4 pi epsilon naught.
E squared over.
The square of,
Electron.
Okay. It's going to be Q1 times Q2.
Which is
So it's going to be Q1 times Q2 over.
R.
or
Where?
mu, the
just the
distance,
distance between.
or the distance.
I don't
between-
need mu.
You need the distance between the electrons.
Okay, I need the distance between the two electrons, which is
R.
the x1 minus x2. X1 minus x2, right? Perhaps I should draw this a little bit better. Let's call this R1. Let's call this R2.
The distance between R.
And this is R, which equals R1 minus R2 in one dimensions, but what we did is we did this all in one dimension, so where I have x's, it could be r's. All right, and by the way, if I were going to include the potential energies here, what would this potential energy be, positive or negative?
That'd be negative.
It would be minus 1/4 pi epsilon naught.
Q or R.
Let's write it. So this one would be 1/4 pi epsilon naught. Then I need a Q1 and Q2. But what is this potential energy between?
Electron in the nucleus.
The electron in the nucleus. So Q1 is minus E.
And Q2 is plus 2.
That's right. So this becomes minus 2E squared. And that would all be divided by R1. And then what would this potential energy be right here?
2e squared over r2.
Yeah, 1 over 4 pi epsilon naught 2e squared over r2. Okay, so those are just on where those electrons are individually. All right? But it's this last term, the electron-electron interaction, that depends upon the distance between R1 and R2, right? Where the two electrons are, or the expectation of the separation between them. And most definitely, instead of them being negative, it's a positive number. So this increases the energy. All right? So, which total wave function has the lowest energy?
The triplet. Right,
That's right.
because you have all three different ones with more potential energy between them all.
Forget about all this term. Forget, this doesn't change. One case to one case. The only thing
But because
that,
they're further
that this
apart.
spatial one, what we're talking about is the expectation between them. The only thing it affects is this one.
Because they're further apart,
If they're further apart,
that means the
This
x1
makes-
minus x2 is going to be
bigger.
bigger, which means it's going to have a smaller number.
It's going to be a smaller energy.
In a molecule, it would be the other way around because the electrons need to pull together to form the molecule. Like
Okay,
fabrication.
yeah, so I mean, so we need a wave function that kept them closer together, that's right.
For H2,
All right.
where helium.
But for helium right now, all right, the lowest energy is when those electrons are as far apart as they can be, right? Because when they're close together, the positive energy gets big,
Right.
right?
Right.
But right now, we want to keep the positive energy as small as possible. So to keep the positive energy as small
You
as
have to
possible, we
separate
want
them.
this to be as big as possible. Which one is bigger? Keeps the electrons further apart?
So negative space.
The negative space one. So therefore, what is the spin situation for identical electrons that is the lowest energy?
True.
The triplet. So in other words, when you have a whole bunch of electrons, what is the lowest energy state for the atom? When the electrons are like this, or when the electrons are like this?
So the electrons have the same spin.
When the electrons have the same spin. All right, and that's called Hund's rule. Where does Hund's rule come from, guys, in words? The total antisymmetric wave function, which consists of a spatial wave function times a spin wave function. And we have two types of spin wave functions, symmetric and antisymmetric. And you put them together. And then the whole reason is that the psi minus space function makes the electrons stay further apart, and having the electrons further apart lowers the energy,
And that gives us the ground state.
and that gives you the ground state. And that's called Hund's rule number 1. So, not trivial to write or anything like that, but that's the idea. Okay? So let's look at some situations. And again, we're going to stick with helium. And what we'll do is we'll discuss figure 5.2. And then we'll talk about the periodic table, I guess. Okay, so let's look at this. So helium. So I'm going to draw helium again. Here's my +2, and then here's my n equals 1. And in my n equals 1, I have L equals 0. And how many electrons can I fit in there? 2, an up and a down. Now, are these going to be both up?
For the lowest energy, yes.
Careful.
You can't put two
So
ups.
You
if
can't.
they're in the same orbital, they cannot be.
Check this out. If I wrote this electron, it would be 1, 0 up. That's this electron, right? That's electron number 1. And if I wanted this one to be an up as well, I would write that as a 1, 0 up. Okay, but these two electrons having the identical quantum numbers,
Have to have different spin.
They have to have different spins, so it's an up and a down in that shell. So yeah, so this comes down to the same thing, that you can't put two electrons in the same place at the same time with the same quantum numbers. All right? So the spatial part, this is the spatial part vanishes
When it
with
comes to
this. Okay?
that spatial part is the exact same, and the half integer spins, then they have to have opposite spins.
That's right. Okay, so let's look at an excited state. So the only possible state we could have here is an up and a down. So S total is what?
Up and down.
So S total
S
S total
0.
equals 0. And what does L total equal? 0 plus 0 is 0. So again, the notation is L total, then S total, 2S total plus 1. This is the way you say it. So L total is a 0, and so a 0 is an S, and the total on S is 0, so 2 times 0 plus 1 is 1. So the ground state configuration of helium is a singlet S. What does the singlet S mean? It means the total angular momentum of 0 and the total spin of 0. Okay?
Would you put 0 for J plus S too?
What's that?
Would you put 0 on the bottom right?
Yeah, so then you can also find out J, and J is going to be the possible sums of L plus S. So you could put down J right here, and it would be a 0. Okay, let's look at an excited state. So let's have, here's our 2. So let's have electron number 1 here, and then electron number 2 here. So number 2, again, I'm labeling, you can't. All right, let's have this n equals 1, L equals 0, S equals a half. And this is n equals 2, and let's have L equals 1, and then S equals a half. Yeah, sorry about that, guys. So this is electron 2, and n equals 2, L equals 1, S equals a half. It's a half. Okay, so let's do that game. What are the possible values of S again here? S total? Well, you can have S1 plus S2 is greater than or equal to S, greater than or equal to the magnitude of S1 minus S2. So what does that mean? That means I have 1 is greater than or equal to S, which is greater than or equal to 0. So S total can equal 1 or 0. Right? The total spin. And here, I don't have to worry about the up and down because they have different quantum numbers altogether. Right? Now, what is L total?
One.
It's going to be 1. It can only be 1.
1 plus 0.
1 plus 0 all the way down to 1 minus 0.
Right.
So L is only equal to 1. So the states that I have here, I know that I have a total L of a P, because when L equals 1, I have P, right? And then what can I have over here for the spin?
A 1, 1, 2.
1 and a 0. But remember, it's 2s. It's 2s plus 1. So it's really a triplet P and a singlet P. Okay? So quite literally what this thing looks like, or what we can imagine is, here's the helium, the plus 2, and here's this one. We can have an up, and then, so this is the n equals 1, L equals 0. And then here's the other level, n equals 2, L equals 1. All right, now, we can have this thing that can be an up, right? Or we could have this one be a down. Okay? Which one is lower energy?
Up.
So this one would be called the